Yeah, hi there. In this tutorial, we are going to cover Cython, using Cython in Jupyter Notebook. So basically, Cython is a superset of Python programming language that gives access to C++ constructs from the Python. So in a way, Cython acts as a bridge between Python and C++. So the overall reason of using Cython in uh, along with Python is that we want to run our code faster. That's the basic purpose. So what I've done is I have installed Cython module, which you can do using pip install, and then I am loading Cython extension using percent load underscore ext and Cython. So how do we define a Cython cell is that we specify this magic function percentage Cython, and then within this everything should be in the Cython code only. So for example, let's say we have a small function which basically takes an integer I, and then it returns multiplying I by this value of pi. It's an approximation of pi value, so simple as that. So so this is defined. Now when we are calling this function, we have to call it like in a normal way, a function name and the value which is passed, and we get the output. So that's how we call a Cython function from our Python from a separate cell, which is a Python cell. Yeah. To know more about this magic Cython, you can use percentage Cython and question mark. This will give you the more details and description about it. So what I'm going to do is cover some basic functions, and let's see the difference between the normal Python function and Cython implementation of that particular function. So we have a function foo which accepts two inputs a and b and just simply returns the sum of a and b. Now if I use a module dis from the library dis, which basically disassembles the compiled Python objects, we will see that uh, this calls load fast. This is actually to load the values for a and b, and then it calls the binary addition. So internally it tells like uh, how 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 the work happens behind the scenes to give you the output. Okay, so now let's say if I want to execute this foo function using Cython, what I have to do is just specify percentage Cython, and I'm just defining the function again just to differentiate between the normal Python foo function and the Cython foo function. So I'm giving Python foo function is just the name as foo, whereas the Cython foo function is cy foo. That's the way to distinguish between, okay, whether it is a Python function or Cython. So that's the normal convention I follow. Whenever I'm creating a function for Cython, I just use cy. I prepend it, okay. And if I time it, so I'm just timing it, that is foo with these two values. It takes around 180 nanoseconds. And if I time it, the Cython foo function, it takes around 140 nanoseconds. So with just simple addition of two numbers, two integers, we can see that it takes lesser time in Cython implementation of foo function, which is 40 nanoseconds are saved. Now let's say because we know in Python we can add two strings also. So let's try to pass two strings. So again, I am using time it to actually find out the time it takes. For, so for the strings x and y, if I'm adding it using by calling the function foo, which is a Pythonic function, okay, it takes around 283 nanoseconds. Whereas the same thing, if we call by using the Cython foo function, using scifoo to add two strings, then it takes around 247 nanoseconds. Again, roughly around 40 nanoseconds are saved. So in both operations, whether it's a normal integer operation or the string addition operation, we see that there is less time uh, involved when we are using the Cython implementation of the function compared to the normal Python implementation. Okay, now let's go a bit further. Let's say we have a function which creates the factorial. So we have a normal function, a Python function. I'm calling it, just to distinguish, I'm calling it as PyFact, which is Python's implementation of factorial, and I'm passing n and returning the factorial value of it. And this is a recursive call, or recursive function basically. So if it is n is less than equals to 1, it will return the 1. Otherwise, it will just recursively call it by multiplying n with the factorial n minus 1. Okay, so in this Pythonic implementation of factorial, I'm just passing 20 to calculate the factorial of 20. It takes around 5 microseconds. Now, now within the Cython cell, I'm specifying two functions. One is the Cython factorial. This follows exactly same logic as the Python factorial function. But the other one, which is the Cython factorial underscore double, what we are doing in this function, we are specifying the data type of the input which is passed to the function, and then we are timing it. If I time the first one, which is the Cython factorial, it takes around 3.99 microseconds. So from 5 microseconds, we came to around 3.99 microseconds. Whereas if we time the second one, Cython factorial underscore double, it takes around 2.52 microseconds. So this is exactly half of the one which was the Python factorial. The only change what we did is we passed the data type of the input, which is to the function. Now let's try to enhance this function a bit more. What we can do is we are passing the data type of the input function, we are specifying the data type of the input function like we did earlier, but at the same time we are also specifying the return type, and we are saying that the function is the C function. So if you are writing a Python function, then it is like def. However, if you are specifying a C function within the Cython cell, then you have to specify like cpdef. So cpdef and the data type of the return, then the name of the function, and data type of the input which is passed to the function, which is an argument. Yeah. And now if we this if we time this function, which is we see we get around 170 nanoseconds. So I mean from 5 microseconds to 170 nanoseconds, so considerable improvement. The only thing that we have done different in this case is we have specified the data type of the argument, which is of the argument to the function. We have specified the data type of the return value of the function, and we are saying that the function is not a Python function, it's a C function. So we cannot directly mm, yeah, so C function here, yeah. So and then we are calling it, and we can see that there is a considerable improvement in the time. Now let's take the same example and apply some looping in it, because in looping we know that it iterates and it takes longer usually. And let's say how it differentiates if we are using a loop. So we have this Python factorial underscore loop, in which we are passing so this is the normal Python implementation of this factorial underscore loop function, and we are passing this n, and then we are ranging it from 1 to n plus 1. So basically it's like calculating the factorial using the loop method instead of using the recursive call. So in the previous functions we made a recursive call, but here we are not making a recursive call. We are just using the loop method and creating the factorial, that is starting from 1 to that particular number. We are just multiplying it, and whatever the result is, we are returning it. So that's a normal Python implementation. And if I time it, it takes around 2 microseconds. Now, if I convert it uh, uh, within a Cython cell in a Cythonic way. So what we are doing is percentage Cython. That's the way to specify that this is a Cython cell. And then what we are doing is we are specifying the data type. So n we know we'll be passing as integer. So so this is the data type of the argument to the function, which is integer, and the output could be in the double format. So I'm specifying the double as a return output, and cpdef is the function which is defined. cdef is when once you declare any object, then we use cdef. So what we're doing is we are specifying the data type of r, and so what basically any variable that we are using. Before using it, we are specifying its data type, or we are specifying its data type at the time we are using it itself. For example, here we are initializing r with 1.0 and we are declaring its data type. Similarly for int, which is for I, which is used in this loop, before using it in the loop, I'm declaring its data type as integer using cdef. Now, if I time this particular function, we see that we get the result in 187 nanoseconds. So this is close to what we were getting earlier, 180 nanoseconds. So just by specifying the data type of the arguments to the function, and data type of the return value of the function, and any variable that is being used, we are first specifying its data type. We can see that we can reduce a considerable amount of time for the function execution. So the reason being, when the Python code runs, it actually, because as you know, Python is a dynamic type language, it doesn't know the data type of the variable until it actually gets a value. So a lot of time it's taken by Python behind the scene to find out, okay, what is the data type of that variable, and accordingly it performs the calculations. But on the other hand, when we are actually specifying the data type, so we are already telling it, okay, that this variable is integer type or double type, then it doesn't have to do that much checking every time. And this has a great impact, especially in the case when we are using loops, because loops runs for multiple number of times, they iterate over number of times. So it doesn't have to do checking all the time, because as we have already specified, we have already told that, okay, this variable is integer or float or any other data type, then that particular step is eliminated to check the data type of the variable. So that's how we see the gain in the performance when we are specifying the data types in the Cython cell compared to specifying the functions in the Pythonic way. Now, if you're already familiar with C, then you must be knowing the different data types available in the C. In case not, I'm just going through it. So we use cdef. So cdef is a directive which tells, okay, that these are the C objects, and also tells the data type of that particular object or the variable. So okay, so we use, for integer we use int in C. For and similarly for long we have long, and for unsigned we specify the word unsigned. Similarly we have unsigned integer. For short data type we use short. For signed, unsigned, we use signed or unsigned word just before that short. Similarly, there is a long data type, float, double, long double, and str is for the strings. Now, one thing is, when we are importing uh, in the Cython cell, so instead of specifying the import, we specify it like C import. We are importing the C implementation of the Python rather than the Python implementation. So if I say import date time, and then I say C import C Python dot date time, so this indicates that we are importing from the Python, and this indicates that C import indicates that we are importing from the C API of the from the actual C function. Similarly, import array, its equivalent in the C is C import C Python dot array. Now we are going now we have checked the basics. Now what we are going to do is we are going to apply these basics to a function where we will try to improve its performance and see how it goes. So this is an example of a spin field. So what we are first doing, we are specifying a random function. This is a normal Python function, random function, in which we are specifying the size of the array, and we are specifying the value -1 or 1. So basically, it will create a two-dimensional array in which the value can be any value can be -1 or 1, and that comes randomly. And the size of the array is what we are passing. Okay, so this creates a two-dimensional array. Now we are using one library from PIL. If you don't have, then you can install this below library, and then from PIL importing the image. Basically, we want to display this grid. What we are doing is we have a function. So these are all normal functions, normal Python functions. So we are not using Cython implementation yet. So this displays that particular spin field using the image.from array. Okay, this is what we get. Now the logic of icing model is that for every point in the grid, what it does, it multiplies the sum of all the spins of the neighbor points with the current spin, and then it calculates the energy. If we see that there is a change in the energy, then it makes a switch. Otherwise, if there is something particularly unlucky, then also it makes a switch. Otherwise, it doesn't make a switch. Basically, it's when I say switch means it changes its sign. Okay. Now this is the Python implementation of this particular function. Okay. So now uh, what we have to do is we have to convert this Python implementation of the function, okay, into the Cython implementation. So let's see how we go about it. Now what we are doing is, so how we are generating this particular image, it's not that important right now, because here we are more focused is how to optimize this function by using Cython, so that we can get the same result in the lesser amount of time, so we can get a performance improvement. That's the more important. Okay, so what we are doing here is, whatever function we had written in the Python, we are just passing exactly same to this Cython cell. So how do we specify it? We just say percentage Cython, and exactly the same code, no changes at all. Okay, and if I time it now, so I'm timing it by calling, this is the function which is the Python implementation, which is icing step. I'm just passing a field to it, which is a two-dimensional array of 200 by 200 size, and this is the Cython implementation. Basically, it's the same function, but the name is given as CY, just to distinguish it between the Python and the Cython implementation. And if we see, the difference is that for the normal Python function, it takes around 718 milliseconds. And if you're passing the same, executing the same function, I mean the same, exactly same logic within this Cython cell, we see an improvement from 718 to 557 milliseconds. So there is an improvement of around 150 milliseconds approximately. Now what we are doing is we are making some changes to it. So from from the normal Cython, I'm just trying to enhance it by creating another function. just it's the same logic, everything is same. What we just doing is we just renaming the function, okay, just to distinguish between the different Cython functions. So earlier was the normal cy underscore icing step. Now I'm just renaming it, creating a new function basically. It's cy underscore icing underscore step underscore fast. So my expectation is that this function should be faster than the earlier implementation of the Cython function. So, and what are the changes I am doing to make it run faster? First is in the previous one we had only mm, uh, we had only variables passed, but and we had not specified the data type anywhere. So now we are going, first thing what we are going to do, as we had already seen earlier, that by specifying the data type of the variables and arguments, uh, we can see an improvement in the um, execution time. So I'm specifying the data type. So first data type I'm specifying is of the arguments which are passed to the function. So what first argument passed is field, which is actually a two-dimensional array. So I'm specifying its data type as long, and the second argument is beta, which is because it's decimal, so I'm specifying its data type as float. Now wherever I'm using the variables like n, m, so I'm specifying the data type using because this is within, this is the C implementation, so we have to use like cdef and the data type cdef int and name of the variable and initializing it. Similarly, cdef int name of the variable m and initializing it like I was doing in the previous functions. So the logic, as I said, is same. It's just that what we are changing is we are now telling the function that okay, this particular variable or this particular argument which is passed to the function is of this data type. So we are just, in a way, we are moving away from this dynamic typing to a static typing, because we are just fixing the data type, and that's how we are expecting the performance to improve, because now there is no need to dynamically check for the type of the variables anymore, because we are specifying it. Okay, so this is done. Cdef 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 for n, m, and n offset, m offset, small n and small m. Okay, everything is done here. Similarly, now this is the Python function, okay, because it is using def. Now this is another function that I am creating here, which is I'm specifying it using cdef. So this is this is the C function. Okay, now it cannot be accessed outside. I'm just trying to access it from this Python function only. And again, I'm specifying the data types of the arguments, and for every single variable which is used is it's declared its data type using cdef. Even the variables, just to note that even the variables which are present in the loop like I, j, so before they are being used, we have to declare their data type. Now, so far so good. Let's run this. Uh, no, so once you execute this, so you basically, in a way, you are compiling this particular code, and after compiling, if you want to check its performance using the time it. Now what I got is this one is the Python implementation that we had already seen earlier. This is the Cython implementation without any modifications, just passing the code to the Cython cell. Now this one is the one which we have just now created, where we had specified the data types of the arguments and data types of the variables like that. So we see from again the Python implementation was taking 745 milliseconds. The Cython implementation was taking 665 milliseconds. But this one, the fast one, which we just now created, it is taking around 90 milliseconds only. So it's within 100 milliseconds. So from 700 plus milliseconds to we are within we have brought down the execution time to under 100 milliseconds. And what we have done, we have just specified, and we achieved this by just specifying the data type. So that's a great improvement in terms of the performance. Now let's see if we can enhance it further. So one thing to notice, when we when we try to Cythonize, or when we try to create a Cython implementation, what we can also do is we can use -a option along with the percentage Cython. That will actually annotate, and it will tell you how the function is, how it is actually performing. So if I add -a to percentage Cython, and if I execute it, yes, currently it is trying to compile, and I think somewhere down the line it will, once it is done, it should show me the output. Yeah, so once this is done, it will show you the output just below it. So wherever you see the yellow lines, so this is like a hint that this particular step of the implementation is taking some time. So this is where we can possibly work on it and try to improve the performance, uh, mostly maybe by specifying the data type of the variable, or by using the, if let's say if our step is using some Python function, that instead of using the Python function, let's try to use an equivalent C function. So that's how we can, so these are the things that we can do to bring down the execution time. If you see plus here, if you, I mean, if you click here, it will expand it and give you an idea. So basically our focus is wherever this yellow line is coming, why it is coming. We can try to go through it, what it is trying to do, and we'll try to fix those particular things and see if we can bring down the time. Okay. Now in this faster implementation, what is being done, I'm just removing -a. Okay. And so in the faster implementation, I've added couple of things. So what I'm doing is, now in the code earlier, we were using like np.exp, that is we were using the numpy's exponential function. Similarly here, numpy.random. So what I'm trying to do now is I'm trying to use an equivalent function of C. Instead of using the numpy's function, I'm trying to use the equivalent function of C. So how to do this? Because we already know that there is a math library. So from the C, so from libc.math, I'm using C import exponential. So instead of using numpy.exponential, I am going to use exponential function from the library, which is from the C. Similarly, from libc, that is library C dot standard library, I'm using C import random. So I'm using a C random function. Now it generates a random function which is actually between 0 and some maximum value, and the maximum value is actually defined by a variable rand underscore max. So I'm declaring its data type also. So cdef extern from limits.h, and this data type is rand underscore max. Now what else I have done the changes? So data type I had already specified, there is no change here. And if I can continue further, this cdef we had already specified in the previous one also, that is we converted it from the Python function to the C function. All these declaration of data types we had already done of the variables. Now the only change that we are doing in this particular faster implementation of the same function is, we instead of using the numpy's function, we are using the C's function. So instead of using np.exp, I'm using exp. So exp from where we got, just as I said, we're getting exp from library c.math, we're using C import exp, and similarly from library c.standard library, I'm importing the random. Now this is done, and if I see the output of that time it, we see that this is, the others are same. If you see, first three are same, like Python implementation, then the basic Cython implementation, then the Cython implementation, which was the faster one where we had declared the data types. Now this is the one where we are declaring the data types and at the same time using those functions which are of C, which are using from C library instead of the Python library. Now you see this time we are getting 6.43 milliseconds. This is a huge improvement from 655 to just 6.43. Now we can try one more thing is uh, we know that the arrays that we are using uh, they will not be crossing the limits. If we are sure about that, then we can also specify uh, so I'm importing the Cython library using C import Cython, and then I'm specifying at the rate Cython dot bounds check false. That is, it should not check the index boundaries at the array. So that is we are sure that the array boundaries will not be breached. That is how we have written the logic, and we are also specifying that Cython dot wraparound is false. That is, arrays will never get the negative index. So this additional information that we are passing, and if we exit, rest of those things are same. And now if we time it, we found that okay, it more or less got 7 milliseconds only, so not much improvement. So basically, even if you don't pass it, it doesn't uh, change much. So basically, the main improvement that we found that when we are using the data type, when we are specifying the data type of the variables of the arguments, and we are trying to use the same function which is coming from the C library instead of the Python library, we can drastically improve the performance of our code. So that's the whole purpose of using the Cython, to improve the performance and make the code run faster. So that's it in this tutorial. Thank you.